Yeah. And we're going to move to the next talk that is quite related. All right. So,
is the mic working?
Okay. So Kaliroe Pappas is going to tell us about how to make from these theoretical ideas into something more down to earth. So please go ahead.
Yeah, unfortunately, it'll be very down to earth. But yeah, I'm Kaliroe. Please ask me how to pronounce my name as much as you need. And I'm talking about abracadabra. So I'm going to start with talking about abracadabra and axions. Then I'll talk more specifically about our detector, how we are transitioning it to be used for gravitational waves, how we calibrate our system, and how we are modeling our signal. So starting off with axions. So we can search for axions over many different wavelengths, and depending on what wavelength you're looking at, you're going to use a different technique. So for us, looking for axions in the around megahertz region, we use what's called a lumped element technique. And so all lumped element means in our case is that we're coupling to the axion current using circuit components, so inductors, capacitors, and such. So what abracadabra actually stands for is a broadband/resonance approach to cosmic axion detection with an amplifying B-field ring apparatus. We're very proud of our acronym. We are broadband. So just going through really quickly how we detect a signal in Abra, we have our 1 Tesla magnetic field. As Camilla was saying, it's a field-free region in the center, so we only have our magnetic field going through our toroid. The axion comes in, it converts to a current, and this oscillating current, through right-hand rule, induces a magnetic field. And we just place a pickup structure in the center of our magnet to detect this magnetic field. So this is what the magnet actually looks like here, and then this tube, this Teflon tube, has the pickup structure on it. So we've run Abra for axions with 2 different pickups. We had a loop pickup and a cylindrical pickup. The cylindrical pickup helped us to have a stronger connection to the axion signal and produce stronger limits. So the signal we're looking for an axion is this peak in frequency space that is stationary. And it is Doppler shifted by the speed of the dark halo, or the speed of us through the dark halo. And what we can do, which is really nice since it's stationary, is we can take a bunch of data and we can average it down. So we can reduce our backgrounds and maintain the axion signal, which is great. So we've had 2 published runs, and we were able to get just below cast right here. And we've really pushed the limit of our sensitivity with this detector to axions. And so the question is, what do we do next? So in order to get a better axion detector, we need a larger magnetic volume, a resonant readout, and a more sensitive pickup. So since we are limited in space with our detector and cryostat, we're moving to DM radio. So DM radio is going in 3 stages. We have 50 liter right now, which is in the building phase. We're hoping to take data next year. Meter squared, which is in the R&D phase, and DM radio gut, which is in the design phase. So now the question is, what do we do with our detector? And so as Camilla was saying, we're now exploring our sensitivity to gravitational waves. And we'd like to prove that we can search for these ultra-high frequency gravitational waves and axions at the same time to get more funding. So now I'm going to talk about abragraph. But I lied. I'm talking about axions for a little bit longer. So this is what our axion current looks like if we simulate it in COMSOL. We have this nice symmetric circulating current. And this produces a B field in our center in the Z direction. And really easy, we put the pickup there, fine. The gravitational wave signal, as we've discussed at length, has a very, very strange looking current in our detector. And this makes this B field, which is coming out in the, if our wave is coming in on the x-axis, in this up and down position. So in order to detect the gravitational wave, we use a figure-8 pickup instead of a circular pickup. So we've tried 2 different experimental setups. We've tried one with 2 gravitational wave loops in an axion loop, and we've tried one with just one of them. And the reason we've tried 2 all comes down to calibration. So that's the next section. So this was our first setup. We have our figure-8 calibration loop here at the top. This is set 45 degrees from the other 2 loops. So the idea is this 45-degree calibration loop can couple into our 90-degree loop at the top and our 0-degree loop at the bottom. So therefore, we can calibrate both of these loops together. We unfortunately can only take data on 2 loops at a time because we only have 2 squids and we only have a 2-channel digitizer. So for the first run, we were intending to do 2 runs, and the first run would be these 2 top loops here. So calibration is extremely important in any experiment, but we really need to prove that we can calibrate both of these loops independently. And so to do this, we have 4 different calibrations that we need to do. We do 2 end-to-end calibrations where we calibrate the pickup with its intended signal, and 2 cross-calibrations. We're calibrating with the unintended signal. Okay, I'm going to be showing this.
Sorry, when you say intended signal, how do you generate that intended signal?
Yes, so if we go back here for the axion signal, we have this calibration loop here, and we put a current through it, which should make a magnetic field in the center, and we can pick that up with our pickup loop here, and the gravitational wave here with the 45-degree loop, that is mimicking a gravitational wave signal.
Cool, thank you.
Mm-hmm. Okay, so what this is essentially our dilution fridge. So if we start out here, we are inside the magnet, and we have our pickup loops and calibration loops. Then we go up to our mixing chamber plate where our squids are sitting, and then these are just SMA connectors. All of the loops connect either into the SMA connectors or the squids through a twisted pair. And then up here we have our wires. I just put inductors here to say that we do have parasitic inductances between our wires. The calibration wires are just coaxial wires, and the squid wires are covered in a steel mesh. Oh yeah, and they lead out. Oops, I should go back. They also lead out to our ports at the top. Looking just at the gravitational wave pickup loop for now, we have our cross calibration where we put the signal in through here. The idea is that the pickup would read, or rather not read, the signal and then be read out down through our squid electronics. And same idea now with the end-to-end calibration, except we expect a much stronger signal here. Unfortunately, we did not see that. What we saw was that our axion calibration signal, which remember this is the cross calibration if we're talking about the gravitational wave loop, was actually stronger than our gravitational wave calibration. So this makes absolutely no sense because what we expect to first order is that the mutual inductance between these 2 loops, oh, this is so uncalibrated, speaking of calibration, it's supposed to be 0. And we're seeing this really high correlation. So there's got to be some amount of parasitic inductance in our signal. It could be through our pickups, through the twisted pairs, through the squids, or through the wires. It could also be through our Magnacon electronics. Not sure. Yeah?
So from the diagram we were showing before, does that mean that between the different calibrations you need to warm up the system, then reconnect things and cool it down again?
Thankfully, no. So I keep showing these so I could just go to the next slide. We have a terminated, we terminate the port of the calibration loop not being used. If we had to warm up between these, it takes us about 3 weeks between warm-ups. Mm-hmm. We would never finish. So yeah, we just use a 50 ohm terminator on whatever calibration loop is not being used, and then when we run, we terminate both ports.
Okay.
Yeah. So, right, so now I've made this really messy. I put in a bunch of different mutual inductances you could possibly think about. So when we look at this current path, you can see there's actually quite a few different ways that we could be coupling between these 2 pathways. So what we did is we did an inductance run. So this time we did warm up. We had to do that for this one. And we disconnected 1 calibration loop and 1 of our squids. And so the ones we left were the axion pickup and the gravitational wave calibration, so we just left a cross calibration. And so what we did is we ran a signal down through one calibration port, read out through the other to test for parasitic inductances. And we did the same cross calibration. We did 4 calibrations for this. We also did the end-to-end, which are no longer end-to-end in this case. And what we saw was that if we look at the connected pickup loop, the signals are extremely similar if we have a connected calibration or we have an unconnected calibration. This is log scale, so even though these two look like they're separated, they're really not separated by much. That leads us to believe that a lot of the signal that we're seeing here is actually coming in after the twisted pair, because the twisted pairs are not connected. And then for the unconnected squid, we are also seeing a signal here, again confirming the idea that, I think I said those backwards, but we're seeing a lot of parasitic inductance on the wires and possibly on between the magnetron electronics. We're not seeing it really between the pickups. So when we look back at our really, really messy plot, we're seeing that this is providing most of our signal, and we can't really say anything about any signal that might be coming from our loops. And that is what we're using for our calibration. So this brings us to our second setup. So the first thing we did is we reduced the amount of loops. There's a few reasons for this. The most basic reason is if we can't calibrate our top loop, we have no chance of calibrating our bottom loop. And more wires, more problems. It's always better to remove wires if you can. So we removed our bottom loop. We also moved our calibration loop closer to our pickup by 5 centimeters, or by 4 centimeters. It's 5 centimeters to 1 centimeter, and we rotated it to be in line with our pickup. So our mutual inductance from COMSOL calculations and back of the envelope calculations were 2 orders of magnitude better. And then what we also did is we distanced our twisted pairs. So many of you might be thinking they're twisted pairs, they shouldn't talk to each other. You are correct. But where our twisted pair connects to the Teflon tube, there can be a little bit of a wire gap. We try to minimize this as much as possible, but if they're all sitting on top of each other like they are here, they have the most chance of talking to each other. So by distancing them, we're giving ourselves the best chance possible. So this is the new setup. We have just our 4 loops, our 2 calibration loops, with much stronger mutual inductances. And we saw huge improvement. So on top, we have our first configuration, where this is just for the gravitational wave pickup. Our axion signal and gravitational wave signal are virtually the same, with the axion signal being higher. But here we see much significance with the gravitational wave signal that we are putting into our detector. With a 2 orders of magnitude difference, we are confident now that we are actually seeing a signal between the calibration loop and the pickup loop. So this is the schematic of our calibration. We have a signal generator, we put a signal through, and we read it out all the way to our digitizer. We understand pretty well this connection here, signal generator to the current loop. We've measured this while warm. Just the attenuators that we put in our system. And so we know this part pretty well. And so what we get from our calibration is what current on the pickup looks like being read out. So this is the information that we are getting from our calibration. So now we move to signal modeling. So we use COMSOL to model our signals, and we use the equations provided to us by our wonderful theorists, all of whom are at this workshop. They gave us a full page of equations that we got to enter. And it looks very interesting. We do have the surface currents that Camilla was talking about included on our simulation. And so since this signal is directional, we do have to model it coming into our detector from different directions. So we do take advantage of symmetry, and we only model over a quarter of the sphere. It's not an eighth of the sphere because our loop is not in the center. It's 1 centimeter up, so we do have to do the quarter. So what this gives us is our COMSOL modeling gives us how we get from strain to our pickup. And so now if we combine that with the calibration, now we have a full picture of how we can get strain read out into our digitizer. And so you've seen this image now from the previous talk from our wonderful theorists, giving us a very optimistic projection of what our sensitivity could be. I have yet to calculate what our sensitivity actually is. For now, we'll show this picture. And also for the DM radio suite, you can see we're going to be able to get much, much deeper in strain. I personally would like to reach super radiance because then we can take an axion detector converted to a gravitational wave detector, detecting gravitational waves from axions. Don't know if this is possible. I'll leave that to the theorists to make this happen. So our frequency range is from 10 kilohertz to 5 megahertz. This is subject to noise. It's actually a little bit more narrow. This is just the position of our filters. And we're using primordial black hole mergers as our signal template. Don't come at me. This is a LIGO template. It just looks much nicer than my template, which is why I use it in talks. And so in order to take our data, we're taking time series data because these signals are transient in 2 channels, and it needs to be compressed. So this statement sounds very trivial. We had to rewrite our data acquisition system. So this took a really long time to do. The data is huge. I think right now we're getting about a terabyte a day. For us, this is big. I realize saying this at the LHC means nothing, but we have a computer, and that's what's taking our data. The templates are created using the Ripple code base. Thank you, Valerie. And our frequency range limits the possible masses, and our distance is going to limit our sensitivity. This may mean that we are looking for primordial black hole mergers at Harvard, but if we don't check, who will? So we have 2 options for our searching. We can do a chirp search. This means no averaging. And remember before I was talking about the axion signal and how wonderful it is that we can average it down and get our backgrounds down. In this case, we couldn't, and this would be a time domain search. But the strain is higher for a chirp search. As opposed to an in-spiral only search, it's less sensitive, but we could do some amount of averaging. Of course, with the averaging in this case, we have to be very careful depending on the duration of the signal. So we would be using a moving window averaging. And likely this one could be done in the frequency domain. So current status, we've done all 8 calibrations. We do both magnet on and magnet off. And we are currently collecting data. I'm frantically checking that it's still working every few minutes, having nightmares about the magnet quenching. But we're collecting now for a week. We'll be done on Sunday. Yeah, thank you all for listening. On the last slide, it decides not to do this. Well, I was going to say thank you to my collaboration, but I guess I won't.
Well, we say thank you to you anyways.
Yeah.
Thank you. Yes, Joachim?
Can you comment a bit on what the dominant noise sources are? So what do you think will ultimately limit the sensitivity of this approach?
Yeah, so we have a lot of noise in our detector. And right now, our dominant noise is EM noise. So we do have a superconducting shield. That's what's down here that protects our magnet. We're also covered in mu metal. And despite all of this, we get a huge amount of electromagnetic noise. We can actually read out radio stations.
So you mean electromagnetic noise from the outside, not noise that comes in through your whatever power supply, whatever?
It's probably both. But we know for sure that it's coming from the outside as well. We've done, back a few years ago, we did a few tests where we put extra mu metal shielding around our detector, and we did see a slight reduction in the noise. Yeah, the fact that we can read out radio stations means that we don't have perfect shielding. because otherwise we wouldn't see them.
So is there ways of improving the shielding, or would the way to go then be to go to a particularly radio-quiet location somewhere?
I mean, ideally we would go to a radio quiet location, but I don't think that the funding's there for that. We could try to improve our shielding, especially shielding our electronics, as you mentioned. So that is one thing that we are taking into account for DM radio, for sure, in 50 liter. We have our readout shielded very well and held at a colder temperature. So we also do see vibrations because we are low enough frequency. Most of these are below 10 kilohertz. So a lot of that gets filtered out by our high pass filter. We can stomp on the ground and see it very easily. So there are harmonics. But yeah, we're definitely very noise limited.
But these all sound like noise sources that are at least in principle reducible.
Yes, yes. And we do have some vibration reduction or mitigation. So I don't know if you can really see it in this picture, but our magnet is actually hanging from a Kevlar string. And then it's connected at the top with a steel spring. So it is on a pendulum.
Cool, thank you.
Hello. Oh, thank you for your talk. And I have something to discuss about the theoretical side of your talk. Maybe go back to page 21. That also goes to Camillus as well. He often mentioned about the discussion yesterday, and that discussion centered around that equation. And so the whole point of this gravitational wave abracadabra experiment is the analogy between the axion and the gravitational waves.
Yeah.
That the even axion can be handled using the effective currents. But for the gravitational waves, that is incorrect. I have been raising, even in yesterday's discussion I raised, but very difficult to penetrate the authors. The point of the gravitational waves, or any kind of gravity, in Einstein's gravity, is that it modifies not only the inhomogeneous equation, but also homogeneous equation. And persuading, there are more equations you have to handle, not only that. And even that equation is not correct. And persuading referee was more easier than persuading the authors, must be.
I'm going to claim experimentalist on this.
So that also belongs to, Camillus as well. So referee has asked us to, demand us to explicitly mention where the previous authors went wrong. So we did it.
I think we should use the general discussion session for this and do questions for Kaliroe right now.
So let's keep it on the hold for in 5 minutes. We'll come back to this. Juan?
So I have an experimental question, even though I'm a theorist. So can you mention, maybe you did already, but what was the sampling time and the integration time for this experiment?
So we have a 10 megasample per second digitizer. So this limits us to 5 megahertz if you go to the Nyquist frequency, and we put a low pass filter there. For the Axion runs, we ran for a month. But now we're collecting a terabyte a day. We're going to run for a week, especially since we're looking for these transient signals, and we're not going to set any very impressive limits. We're looking to be able to reproduce the Axion analysis, just to say we can do it again for DM radio. But yeah, about a week. Yeah.
Is that going to improve in the future, or you're going to keep the sampling time also?
For DM radio? DM radio, we are sampling 50 liter at, I think we're 25 megasamples per second, but let me go back. 50 liter is in a similar frequency range. Here we go. So it goes a little bit above Abra, but not much. Where we're going to see a huge jump in our sampling rate is going to be meter cubed.
Nancy?
Yeah, thank you for your talk. I have a calibration question. I'm a calibration junkie. So I think I didn't understand your flow chart. Are you saying that you're relying on COMSOL for some of your ultimate like calibration from strain to voltage?
Yeah, so when we're talking about, so this goes back to the geometry of the system. Our calibration is very good for understanding the system response to a current, but the actual gravitational wave current has a different geometric coupling into our system than just the wire. So we do the COMSOL simulation. I don't know if it's actually helpful to go back to that flow chart. The COMSOL simulation allows us to know how the strain creating an effective current in a magnet would get to the pickup.
But isn't that highly dependent on your exact geometry? Because maybe you have some like non-cylindrical symmetry in the actual experiment, so your strain to current calibration, like your model is going to be like an ideal experiment, whereas your reality is not an ideal experiment.
I would agree. Our error on this is probably in like, we tack it into our general error, like 1 or 2%. But when you're talking about the difference between maybe imperfections we might have in our magnet modeling versus what a current in a figure 8 looks like versus the current in our magnet, we're getting much closer to the actual system by modeling in COMSOL.
Yep, Valerie.
Yeah, thanks. Great talk. And all criticism of theorists is absolutely absolutely correct, right?
No criticism from us.
So it'd be very, very interesting to kind of see what the sensitivity curve that you kind of get in the real world as opposed to on paper. I think that, I mean, even if, as you say, right, you're looking for black holes at Harvard, right? I mean, I think just kind of seeing to what extent we're too optimistic here, I think is super valuable. The question I had, so you, if I understand correctly, you're doing the search using templates, right? Basically the way more or less LIGO does it, which I was just wondering, like, because that's like difficult in the sense that you need a template base and all this, right? I wonder how much you gain doing that compared to just kind of looking for spikes or something in your data.
So the issue with looking for it, we gain a lot by looking for a unique looking system because of the amount of noise we have. When you talk about looking for a spike or something like that, I can give you spikes. I can give you plenty of spikes. So we actually do gain by looking for a unique system. That's also with the axion shape. The fact that it is such a unique shape helps us a lot in our search.
In a fantasy world, right, where you had the 2 loops, or maybe even in a real fantasy world, 2 detectors, and you looked for coincident spikes, do you think that would, like, kind of a bit the way Mike was?
So I would be. If you look for coincidences in our system, let's say you have the 2 detectors, we somehow have funding, we have 2 cryostats next to each other. The radio stations would also produce a coincidence. Someone turning on some system in our building, that would also produce a coincidence. I would be very skeptical.
Separated.
Yeah.
All right. So is there any other question for this talk specifically? No. Okay. So if not, well, you can stay there and we can now open the floor for the more